All right, so if you remember, the endpoints of a chord in a circle are also the endpoints of an arc. Right? I mean, it makes sense. The endpoints of a chord would also be the endpoints of an arc because the endpoints of a chord are on the circle. And this theorem right here relates the subtended arcs. Now, subtended, remember, means to be opposite of or to establish the boundaries of something. The subtended arc of a chord is opposite of the chord and shares the endpoints. So to subtend, we're talking about being bound by the same endpoints, essentially. The chord and that arc are subtended. They're bounding each other right there. So here it says, in the same or congruent circles, congruent arcs have congruent chords. And then the opposite here, in the same or congruent circles, congruent chords have congruent arcs. And that just makes sense. We're equally spaced amongst the circle, so that arc that it creates from those endpoints, if we know that that arc is congruent to that arc, we know then that that chord would have to be congruent to that chord. And we do know all of this because those central angles are congruent. So here, use the figure to find the measure of each arc. Well, I know that they are bound by the same endpoints of congruent chords, so those arcs must be congruent. 6x equals 4x plus 34. That means 2x equals 34. X is 17. So if I plug that in, 6 times 17 would mean that this arc right here is 102 degrees. And so that arc must be the same thing. They're both 102 degrees. Here it says, to construct a hexagon, Akira marks a 60-degree central angle on a circular piece of cloth. I thought it was a she. I've taught Akira before. She was a girl. Very confused. Anyways, he draws the chord, subtends the angle, and measures it. Then, starting at one endpoint of the arc, he draws another chord of equal length. What kind of hexagon will this process create? Well, if one is 60 degrees and he's creating a chord and then he's copying that chord over and over again, well, all of these are going to end up being 60 degrees central angles. Every single one of them is going to be 60-degree central angle. And so he's creating a hexagon that is going to be regular. All of these chords are going to be the same. This is going to be a regular hexagon. Well, if this is indeed a regular hexagon, then we know these chords are the same. I can find the length of each chord here. 3x plus 25 equals 6x minus 11. I can solve for x real quick. This would be, I add that, that'd be 36. 36 equals 3x. So x comes out to be 12. And notice here, if these are all congruent, well, I know that these are going to have to be congruent angles. Every one of these angles is going to be congruent. So that means this is not only an equiangular triangle, we know it would also have to be an equilateral triangle. See all that? If this is 60 degrees, I know a hexagon forms 120 degree angles, so both of these would have to be 60 degrees. And so this is an equilateral triangle, which means that these side lengths are congruent to the side length of the chord. So if I want to find the radius of this circle, it's the same thing as the length of the chord. I know I said all of that, but take a second and look at it if you need to. I can plug this in to find the length of the chord. I know it's going to be the same thing as that radius. 6 times 12 is 72 minus 11. This comes out to be 61. The length of the circle is radius. is 61. Whatever units we're measuring this in doesn't look like they have any kind of units on it.